So I want to revisit our conservation of energy. I am going to add in the heat term. We didn't need to include heat previously because it is something that takes time. A ball rolling down a hill doesn't have time to exchange energy between the system and surroundings because they're at different temperatures. So remember that heat is a transfer of energy due to the system and surroundings having different temperatures. This takes time. It's not something that happens quickly. You putting a pot on the stove, turning the stove on, that is a way of transferring heat. That happens faster than just the stove sitting in the room. And if the pan, if the pan and say water in the pan are at a different temperature than the room, they certainly will have experience a transfer of energy by way of heat. But of course, turning the stove on will transfer that energy faster. Work is still integral of force dotted with ds, so it's forces other than gravity and a spring, because we've accounted for those in the potential energy terms, but forces acting as an object moves some sort of distance. What we're going to talk about is conservation of energy in terms of gases. With gases, these potential and kinetic energy terms are still totally applicable if we're talking about, say, our container of gas rolling down an incline or rolling up an incline. If the container as a whole is changing height, we would account for that in the potential energy terms. If the container as a whole is moving, we would account for that in the kinetic energy terms. For all intents and purposes, right now, we're going to go ahead and assume our container of gas is stationary. So it's not moving. It won't change height. It's not connected to a spring to oscillate. Under that assumption, then the container as a whole will not have any potential energy or kinetic energy. So we're left with any work done on the gas. We don't tend to write the external piece because we're now left with only work done by forces other than gravity and a spring. That work plus any heat transfer, so energy transfer because of those temperature difference, will equal the change in thermal energy. This equation right here is called the first law of thermodynamics. It is conservation of energy for any gas system. The gas could be going through a variety of processes. It could be a constant volume, constant pressure, just constant stuff. This equation must be satisfied in dealing with our ideal gas processes. Now, heat we've already mentioned in the previous slide. We have two different equations for heat. We have an equation for specifically a constant volume process, and we have an equation for a constant pressure process. Outside of these two equations, we would have to have enough information to come back and use the first law of thermodynamics in order to find the heat. So we're going to walk through these different quantities and look at different equations that come to play depending upon the gas processes. Now, thermal energy, we can also call that the internal energy of the gas, because the thermal energy is always directly related to the temperature. The temperature determines how fast, on average, the molecules are moving around. Now, there's molecules moving at a variety of different speeds, different directions, but on average, that speed is directly related to the temperature. It turns out it has to do with what is called degrees of freedom. And this is different based on whether our gas is monatomic or diatomic. As a reminder, monatomic is gas molecules that stay as individual atoms. They do not bond together. The thermal energy in a monatomic gas is 3/2 nRT. So not the change, that thermal energy at a specific moment in time is equal to 3/2 nRT, where N is our number of moles, R is our gas constant, T is the temperature of the gas. The 3 in the numerator represents what we call the 3 degrees of freedom. If we think about how the molecules can be moving around in the container, well, we're talking single atoms, so they're going to be moving roughly lines. They could be moving in the X direction, the Y direction, the Z direction. That Z is supposed to be kind of coming out of the page. I don't draw 3 dimensions very well. This is where the 3 comes from, is the allowed or possible directions of motion. Now, granted, the motion doesn't have to be along the axes. It could be at some angle, but that still boils down to X or Y or Z or a combination motion. So we have 3 degrees of freedom. In terms of this first law of thermodynamics, we would say delta E thermal is equal to 3/2 nR delta T. The thermal energy or internal energy changes if the temperature changes. This is specific for a monatomic gas. A diatomic gas, where we have 2 atoms bound together, they end up with 5 degrees of freedom. So not only do they have the X, Y, Z motion, but because these molecules are bonded to each other somehow, they could bend around this bond up and down, or they can twist. I don't know how to draw twisting on this picture. So they can bend around the bond or twist. Kind of like you're opening a bottle and you're twisting the jar, one of them twisting relative to the other. So they have the 3 degrees of freedom because of XYZ motion, but then they have 2 more degrees of freedom because of how they can move around their bonds. So we end up with the 5/2 nRT, So delta E thermal, the change in thermal energy for a diatomic gas, will be 5/2 nR delta T. Now, let me go grab the picture from the test notes where we have CP and CV again. So I showed this clip from the test notes in the previous video. This is where they talk about the degrees of freedom, the thermal energies, 3/2 nRT for a monatomic gas, 5/2 nRT for a diatomic gas. But because we get this 3/2 R and 5/2 R, and that has been defined as CV as well, it turns out we can write the change in thermal energy as N, the number of moles, CV, this constant, this molar specific heat at constant volume, times the change in temperature. So this equation right here, the NCV delta T, is a generic way of writing the delta E thermal. We do have to know if the gas is monatomic or diatomic in order to use the equation though. Similar to our heat equations. These heat equations, we also need to know if the gas is monatomic or diatomic because these constants depend upon which type of gas we have. Okay? Now, the third term in this first law of thermodynamics, work. Let's talk about work here for a second. We're talking work done on a gas or by a gas. So if work is done on the gas, that means energy was transferred in to the gas. We are still going to use the sign convention we used in earlier chapters, that positive work means energy going in to the system. We will see work done by a gas. Sometimes it will say on the surroundings. If the gas is doing the work, that means energy's leaving. So energy's out, which we will use the notation that work is negative. So similar to before, if we're adding energy to the system, positive work. If we're taking energy away, negative work. So as a reminder, work, as we talked about it before, was an integral of the force that's being applied dotted with the displacement. So the force had to actually be acting along the line of motion in order for that particular force to be doing work. So the dot product, if you remember, it was only the component of the force parallel to the displacement that was doing work. Well, as we think about a gas, let's say I have a container, like a bicycle pump type container. This gas has a piston of some sort and a handle I can push inwards or pull outwards, either way. If I were to push, so I'm applying a force, pushing on this piston, causing it to move. If I'm pushing down, then the motion is going to be down. This would be our ds, so our infinitesimally small displacement that we're talking about, and then F would be the force I'm applying. But again, with gases, we don't typically talk about forces, we talk about pressure. So pressure we know is force per area. If we were talking about the pressure that I was applying, essentially, so the pressure that I'm applying, but the pressure that the gas experiences because of the force I'm applying, that pressure would be the force divided by the cross-sectional area of the piston. So my applied force would be the pressure I'm applying times the cross-sectional area of the piston. So if I plug that in for the work, now the force is in the same direction as the displacement, so I don't need to worry about the dot product. So integral of pressure, we have our cross-sectional area, so pressure times area was the force. ds is talking about the small little distance the piston ends up moving, which in turn is moving some of the gas. Well, if I take the cross-sectional area and multiply it by a very small change in height, that ds, this actually represents dV, meaning the small change in volume. We can say work is the integral of pressure with respect to volume. We have to change the volume. The piston has to actually physically move to do work. Just like we talked about earlier chapters, the force had to cause motion and it had to be acting along the line of motion, or at least a component. Same thing, this pressure has to cause some sort of change in volume. Now, you will see a negative sign in the equation. The reason why is, if we're going to stick with our same definition of positive work versus negative work, well, if my pressure is increasing because I'm pushing down on this piston, then the volume's decreasing. So the pressure and volume are opposite in sign. To get a positive answer for our work, we need this negative sign in the equation. So the negative sign is just making sure that an increase of pressure in the gas, which in turn causes volume to decrease. To get the positive answer, we just need this negative sign in the equation. So this is our fundamental equation for work. Done on or by a gas. If you think about integration in general, we were talking when we introduced processes before about a PV diagram. Some sort of diagram where we have pressure on the vertical axis and volume on the horizontal axis. Any one point on this diagram represents a specific volume and a specific pressure. A process would be how we get a gas to go from one state to another. So our different processes we talked about isochoric, meaning constant volume. We talked about isobaric, meaning constant pressure, and isothermal, meaning constant temperature. These are the specific processes we talked about. Isochoric is always a vertical line. So for example, if we started at this P1V1 and let pressure decrease, but maintain the volume, it would be a vertical line pointing downwards. We could have a pressure P1 and increase the pressure. If we increase the pressure, but still held volume constant, it would be in a straight line pointing upwards. Integration. Since here we have a graph of pressure versus volume, the integral represents now the negative sign, so the negative area under the curve. Isochoric, because the volume does not change, there is no dV, work is always 0 in an isochoric process. That pressure has to cause a change in volume to have work being done. And definition of isochoric is that the volume is not changing, thus there's no work being done. Which means if we go back to the first law of thermodynamics, if there's no work being done, then the change in thermal energy has to be equal to the heat. So we're going to have a few different relationships that come about because of these processes. Constant pressure. Let's come over here and look at isobaric, or constant pressure. PV diagram. Again, any one point on this graph represents some sort of specific volume and pressure. Isobaric means keeping the pressure constant. So my graph would be, well, the volume could increase until we reach a final volume. Or we could also have the volume decrease until we reach some other volume. So an isobaric process, the PV diagram is always a horizontal line. Area under the curve is just a rectangle. Well, the integral works out easily because if pressure is a constant, we can pull that out of the integral, and that leaves us with the integral of dV. Since V, volume, is our variable, we're integrating from a V initial to a V final. So the work becomes negative P, integral of volume, or well, just dV, is simply the volume, but then we need to evaluate this integral between the limits, and we end up with V final minus V initial, which you'll see this written as negative P delta V. Very simple to find the work done in an isobaric process. But this equation is specific to an isobaric process. If we want to carry this back to the first law of thermodynamics, if pressure is constant and Q is NCP delta T, work is minus P delta V, we can relate that back to the change in thermal energy. The last process is this isothermal. Isothermal, if you remember, it's this hyperbola looking thing. The work is still totally the area under the curve. And by the way, if the function points to the right, work is negative because we're increasing the volume. If the function points to the left, work is positive, meaning work is done on the gas. Doesn't want to write it. Come here. Work done on the gas, energy into the gas. Sorry, I just hit the magnifying glass button. Energy in to gas. If the function points to the right, work is negative, meaning work is done on the surroundings by the gas. So energy's out of the gas system. We do end up with a specific equation when we're talking isothermal. Work, the fundamental equation is still the integral, negative integral of P times dV. But when it's isothermal, we know both pressure and volume are changing. As pressure goes up, volume goes down, and vice versa. So we need a way to relate pressure to volume, because to do the integration, we need V, volume, in the function to know how to integrate. Well, we know pressure and volume are always related in the ideal gas law. So we can say pressure is nRT over V. Since all of our processes were assuming a constant number of moles, R is always constant, and in an isothermal process, the temperature is constant. When we plug this in, it's only the volume that's changing. But again, this is specific to the isothermal process. So we can pull out the nRT. Our limits are still from a lower limit of some initial volume to an upper limit of some final volume. Integral of 1 over V is going to be the natural log of V. So we end up with negative nRT times the natural log of V final minus the natural log of V initial. The natural log of a number minus the natural log of another number can also be written as the natural log of V final over V initial. So the first number divided by the second. Now there's a lot of different individual equations. So when you look in the test notes, I'm going to go grab the table. There's a very nifty table that pairs specific equations to their specific processes. All right, so this was specifically for the isothermal, meaning constant temperature. This table is in your test notes in chapter 19. These relations we talked about in chapter 18, the previous chapter. We've talked about just a sealed container where it's only the number of moles that are staying constant, constant volume, constant pressure, constant temperature. We have not talked about adiabatic yet, but we will in just a minute. The nice thing here, every row, I'm just circling constant volume. The equations in this row are specific to this process. So our relationship, temperature over pressure at some initial moment in time needs to equal temperature over pressure at a later moment in time. As we just mentioned, work is 0 if the volume is not changing. And then our heat equation, the NCV delta T. On this same page, if you scroll up, is where that little table I showed you for CV and CP, where those are located as well. So each row has equations that are specific to the process, which is very nice. This top row has the generic equations that always work, meaning the first law of thermodynamics. When they show that this also equals the NCV delta T, that's what we said when we said the change in thermal energy is NCV delta T. These equations are always true. They just modify based on what we know specific to the process we're talking about. Constant temperature, isothermal. Here's the results of the integral we just did. But notice, isothermal means delta E thermal is 0. Again, that's because delta E thermal is always directly related to the temperature. And so if the temperature is not changing, then that internal thermal energy is not changing either. What that means, if we think about this first law of thermodynamics, 0 would equal work plus Q. So whichever one I bring to the other side, the work would be the opposite of Q. It would be negative Q. This is a little counterintuitive in that we usually use the word heat in our normal lives to talk about temperature. And so it is a gut instinct to think heat. If you don't change temperature, then you don't have heat. But that is not the case. Heat, we could have our container being heated by some sort of burner, some sort of flame. There can be energy exchange between the system and its surroundings because they are at different temperatures. But isothermal also means that if there is heat, then there's work being done as well. So if energy is being put in, then work is also being done, meaning the volume is changing somehow. So just make note for yourself that having no change in temperature doesn't tell us the heat, it tells us that the thermal energy is zero. Now this last process is called an adiabatic process. It's defined as no heat exchange, no heat transfer. And so there's no energy exchange between the system and its surroundings. So either the process is extremely fast, so there's no time for that heat to flow, or it's so incredibly slow that the process just never seems to change temperature. That the system and its surroundings always appear to be at the same temperature, essentially. The equations that apply. We have pressure times volume to, this is the Greek letter gamma, to the gamma power. It is just the volume that is to the gamma power. But pressure times volume, that volume to the gamma power, at any one moment in time has to equal that same relation at a later moment in time. Gamma is equal to these constants, the molar specific heat at constant pressure, divided by the molar specific heat at constant volume. Again, the top row is going to be the top number. We end up with 5/3 for a monatomic gas, and we end up with 7/5 for a diatomic gas. So these are constants. This is on the test notes. It's exactly where you see it relative to this table that we're looking at. So a big part of this section is just knowing how to use these equations and when to use the different equations. So I'm going to do some examples and go through as many as you need to have a better understanding.